The final speaker will be our colleague Václav Jirkovský, who will tell you something about the knowledge representation and knowledge management using semantic web technologies and ontologies. Very useful thing in all companies, probably.
So, thank you for the introduction. So, semantics for knowledge management in production. In our research group, we are working with semantics for maybe 14 years. And nowadays, we see many big industrial companies which are focusing on the semantics in various projects. We had several projects with big companies about the semantics with the Ford company, Airbus company, or from the beginning of our research group with Rockwell Automation R&D here in Prague. Sorry. So, introduction. Maybe you know better than me that manufacturing is changing during the time. You can see from the dating of the slide that still valid. So we have several KPIs like time to volume, time to market, very rapid product introduction to the markets with increasing volumes. Products becomes more complex, greater level of miniaturization, offering personalized products, small batch production, etc. So these all of the aspects are the aspects of Industry 4.0. We have many interesting approaches, methods, how to tackle, how to solve these problems, but still we have several obstacles. The first one is digitalization of all of the levels of production, of automation, and the second one is integration of the devices, integration of the knowledge, what we would like to somehow process. You can imagine you have different devices on shop floor from different providers, everything with a different communicating with different protocols, etc. It is difficult to somehow integrate it on a syntactical level, and what is a biggest problem is to integrate it on the semantical level. So we can say that the digitalization of all of the levels of the automation, as well as to somehow ensure the integration, is the enabler to employ the new approaches, new trends, and new methods to the automation. Okay, we have data, information, and knowledge. You know that the data, it's a raw facts with no context, just the numbers. Then we have information, data with some context, somehow process data, for example, after some analytic tasks, etc. You can add some value to the data when you summarize the data, etc. But the legacy approaches are able just to represent the data and the information, and the knowledge is typically hard-coded in the control code of the applications of the control systems. It means the knowledge is something what is personal, made from the experiences of the experts, and if you want to change the knowledge which is used for the controlling, etc., you have to change the code, the control code and everything. It is difficult, time-consuming. You need to invite back the company which is responsible for the implementation, etc. So the best way is to use something what is able to represent the knowledge. It means to create some external knowledge base which will be or maybe easily maintained. So it means if you have some change in your knowledge, you can easily apply it and use it in production systems. Okay, I will be talk about the ontologies. One well-known definition is from Thomas Gruber, that ontology is a formal, explicit specification of a shared conceptualization. It's difficult to see what is behind from the definition or what is ontology about, but from other point of view, if you go through the definition, what is conceptualization? Conceptualization is an abstract, simplified view of the word that we wish to represent for some purposes. It means the conceptualization could be everything what is needed in your program, in your application, etc. You can have a conceptualization about, for example, pizza. Pizza is one of the well-known ontology. If you start with ontologies, with a web ontology language, with a protege editor, you will for sure find out that one of the best tutorial for beginners is about the pizza. You can have an ontology which represents spare parts for your production, etc. So what means that it should be formal and explicit specification. So if it is explicit, you have explicitly written, formalized into knowledge-based, and formal specification. It means that it's machine readable. What is important is that the conceptualization should be shared. It means, for example, when you use industrial communication standard OPC-UA, there is something similar. OPC-UA server share the information model with its client to ensure that client is able to understand what is the data about, etc. Here we have an example of the ontology, or not really example, but we can imagine the ontology which represents spare parts of a car. So ontology, a model of some aspects of the word or a specific domain, what is needed for your application. First, you need to introduce vocabulary which is relevant to a given domain, to specify the concepts, the relation, etc. So the vocabulary to somehow annotate the facts, specify the meaning of the terms. So here we have a piston engine. We can say that a piston engine is an engine that is a part of propulsion system. And now we should somehow formalize this meaning of the term piston engine in some suitable logic. So we would like to say that everything what is a piston engine is engine, and in the same time exists some other system which is a part of, and also the system, the second one system is a propulsion system. Okay, we have ontologies, and we need to somehow, or we need to choose some suitable formalism, some suitable language, which we will use for the ontology definition and specification. For sure, you have many different ways or many different means what you can use, but you have to find a trade-off between what is your requirements from the ontology, and on the other hand, something what we can call like user friendliness of the ontology or of the tools what you can use. We use in our research group web ontology language for the defining and specifying ontologies, and it was originated, or what is it behind of the web ontology language is a semantic web. You know that the classic web is a huge library of interlinked document. Anyone can contribute to it, and the quality of the information or even the persistence of the documents cannot be generally guaranteed. It means some server is off or some server is down or document is deleted, etc. On the other hand, World Wide Web contains a lot of information and knowledge, but machines serve just for the delivering and presenting the documents, and you need to connect the resources but yourself. And what is a biggest problem? You need to interpret the documents by yourself. Semantic web, so it was and still it is effort to enhance current web. So we would like to use computers for processing the information presented on World Wide Web, connect the data sources and interpret to data. So we would like to share data, information and knowledge instead of just pure documents. Semantic Web is a collaborative effort led by World Wide Web Consortium, and it's a common framework that allows data to be shared and reused across applications. Because Semantic Web is behind of a web ontology language, the things what are similar to the classical World Wide Web is also valid or is important for web ontology language. It means you have a not guaranteed availability of the document, etc. And therefore a web ontology language is with open word assumption. It means, in opposite to the closed word assumption, what is valid, for example, for the databases, open word assumption means that what is not available or not presented is not considered as it is not valid. It means the definition of a web ontology language files can be distributed across several files, several servers, and therefore it is not expected if one part of the definition is not available, it is not true. This is a technology stack of a semantic web. Important are these four guys. One, or the first one, is RDF. It stands for the definition of the syntax. It means that everything what is used is in the form of the triple. We have a subject, predicate, and object, and therefore ontologies are in the form of the directed graph. The next one is RDFS. It's a schema for RDF. You can use it for creating taxonomies, etc. And the last one is a web ontology language, and it is derived from description or logic, and use it for more detailed, more expressive ontologies. You have possibilities to use it to define their axioms, some cardinalities, restrictions, etc. For sure, there is some querying language, is a Sparkle querying language, and something what is really usable in a situation when you would like to somehow close the word from the open word assumption is to exploitation of the rules, so semantic web rule language. Okay, it was just a short introduction to the what is it ontology and what is it behind. Now we developed during the 14 years several ontologies. One of them is a product process resource ontology. So from the name, it is about the way how to represent products, processes and resources. What is a resource? Resource is everything what is available on the shop floor and or can be used for the production. The motivation is a connection of two different words, not really different, but from the point of view of ontologies, different words, products and machines. So we would like to provide explicit specification of a product and its decomposition. It means to be able somehow represent that we have a final product like a car and the decomposition on every part what is important for the application. And next also specify the related operations and the required manufacturing activities. So operations like assembling, etc. On the other hand, we would like to explicitly specify the second word. It means the machines, the workstation, and also manufacturing activities which are provided by these teams, by these resources. What is the key part of the ontology? It's manufacturing activities. On the one hand side, you have manufacturing activities which are needed for the production of the given product or semi-product. On the other hand, you have manufacturing activities which are provided by the machine, by the resource. We don't want to start it with a specification from scratch. We would like to use some standard which is well known, but as you maybe know, there is no standard which is used in across different domains, etc. So as a cornerstone of the manufacturing activities, we use a standard candidate from US National Institute of Standard and Technologies, maybe, I think, which is called DPPI, Design Process Plan Integration Standard Candidate. It's a little old standards. It is possible to see it from this diagram, but not so really old, I think from 2003. So the conceptualization of the PPR ontology, we have three main parts, the resource part, product part, and process part. The product part, it's used to represent the product and as I mentioned, the decomposition by a relation has part. It means we can create a tree structure of a product on the level of the detail, what is needed for the application. Resource part, so general concept resource, and some concepts like a material, location, human, and the subconcept tool, machine. All these able to execute some manufacturing activities. And from the bottom, the process part, you have a recipe which is related to the product and with a definition of the operations which are required to produce product, semi-product. And these operations are these operations require some manufacturing activities. So you can see that the manufacturing activity serves something like a glue between the resource part and process part. So some examples. Car carpet production. So one of the application of the PPR ontology. So the description of the products, description of the operation related to the products or semi-products and their dependencies, description of available machines and workstations from the shop floor, manufacturing activities, etc. So one of the target or outcome should be something like find out the best production plan what we may use to produce the carpet. Here at the bottom is I don't want to say a definition, but the recipe how you can produce the car carpet after 2 initial heatings, before the forming operations, cooling, etc., etc., some welding operations, mounting plastics, and at the end some inspection. Here you have outcome or output from a Sparkle query. So and ask what is the operation, what is it needed for this operation, which manufacturing activity is needed, some workstation which represent the resource which is able to provide the required manufacturing activities, and the number which is how many resources are available. Okay, from this point of view, this is just a description of the recipe and some of information stored in the ontology, but you can imagine that in some cases you can use or you can specify the recipe to be more complex. Here we have a part of the previous recipe with parallel branches, and in every operation which is required to produce the product, you have several redundant manufacturing activities which are provided by, for example, different resource, different device, or can be provided by the same machine, but for example with a different tool, with a different cost, etc. So, and for us, we have a task to find out the best setting of this or setup of this recipe. It means to choose the best fitting manufacturing activities for every operation. For it, we use genetic algorithms. One of the algorithms which can provide objective optimization. This is the outcome of the optimization. So the advantage of the genetic algorithm is that you have not just one solution, but you can have a set of similarly good solutions. So here, this is one of them with the cost and the duration of the operation, which are selected by the genetic algorithm. Okay, maybe a little bit interesting, a little bit more interesting thing is the production feasibility. So as I mentioned, you have a small batch productions or some different influences which make more frequently changing product specification. Our question is the given product manufacturable with available resources on the shop floor? We can specify 5 different semantic relations between a device and request. The first one is an exact one, so it means that the device and the request are equivalent. The second one is a plugin. It means that the request is a subconcept of the device. In this case, it is still valid for us, but because it is a subconcept, it means that the device is able to provide or is more capable or is able to provide more outputs that you would like to see or have. It can mean additional cost for you. So the best thing for us is an exact semantic relation, but also plugin is okay in some cases, and the rest is a subsume that the rest is a superconcept of the device intersection or disjoint. So we can say that we are looking for resources, machines, devices which are in exact or plug-in relation to the given semi-product or to the given request. This is an example of the production feasibility. Maybe this is an example that we or the application here from our testbed. But on the other hand, we had an application, for example, with an Airbus company where it was from the out of cycle model-based system engineering, when they put or give freedom to the architects to design the aircraft, but the architects are really creative and are able to specify maybe everything, and they should be somehow limited. What is it manufacturable with given resources what they have on their shop floor? It means, for example, you have an autoclave. Autoclave has some dimensions, and if you specify the part which is bigger than the autoclave, you have a problem. It is really expensive to solve somehow, and they wanted to somehow limit them in the beginning of the design of a new aircraft. So in this application from the testbed, we had 3 different parts of track: the cabin, track base, and track bed. Everything or every part, some handle with different dimensions. So we specify the conceptualization in PPR ontologies. So it means the concepts for the robots, concepts for the grills, concepts for the handle of the car, etc. The individuals or instances, it is what is really available on the top floor, on the application. And what is or the relation, what is it here? So it means the exact or a plugin relation is represented by a semantic web rule. So a little bit wordy, but at the end relatively easy to find, specify. Okay, and the last one, a really old example of exploitation of the semantics in shop floor automation is maybe 12 years old example. What we define or with workflow automation is diagnostics, or we can call it production monitoring. Help reasoning is some kind of automatic way how to convert the explicit knowledge from the ontology, implicit knowledge from the ontology to be explicit. Very simple example, you have a conveyor belt A and B, and you have and you would like to define or specify something what is able to say to you that the part fell down to the different conveyor belt and something is wrong. So you can specify a constraint that workpiece is on one carrier at most. So specify by this constraint. And when the piece fell down to the different conveyor belt and is our sensor A2 is able to see the piece on the different belt. With the help of the reasoning, you can see the violation of the consistency of the ontology. The second approach, where you use reasoning for the diagnostics, is not with the consistency checking, but with the classification to some specific class. You can specify a class